All right, we're going to finish up section 2, casting and molding right now, with a lecture on chapter 7, which is casting and molding of plastic materials. So the first thing we want to look at are the common plastic molding processes, okay? So remember with metal casting, we kind of divided things up into the permanent mold and expendable mold categories. So here we're just going to be covering material specific, that is plastic molding, which may take the form of expendable and permanent molds, but the more common processes are going to be permanent mold, plastic casting or molding operations. So first we have gravity casting. Oh, and by the way, the types of processes, whether it's plastic or whether it's metal, the process is going to be more or less the same. Obviously, there are going to be some differences, but the technique, the overall technique for each one of these processes is really going to be the same, whether it is a metal casting process or a plastic casting process. Okay, so gravity casting was one. The second one is injection molding. This is by far the most common plastic casting method. It's also the most common production method in the world. We can just make so many parts so quickly and easily with injection molding, and we'll talk about this later in this presentation. So there's a lot of uses for injection molding. A lot of products are made using the injection molding technique. Then we have compression molding. These can be used to produce small parts. Transfer molding. Rotational molding. We'll talk about this too in this presentation. Dip casting. And then finally, well, I shouldn't say finally, slush casting, and then finally, foam molding, okay? So some of these are permanent, some of these are expendable. But the main ones that we're going to focus on are going to be injection molding and, and rotational molding. So in order to talk about the different plastic casting processes and methods, we first have to understand what we're talking about when we talk about a plastic or polymer, okay? So there's two broad categories of polymers, right? There's thermoplastics and there's thermosets, okay? Thermoplastics look like this. The molecular chain looks like this, right? And one thing that you need to know here, and it may be hard to discern from this image, but each one of these molecular chains are unlinked. That is, they're not linked together. So this is kind of like, imagine taking a handful of cooked spaghetti noodles, right? And you drop them on the floor, okay? So those spaghetti noodles aren't going to join to themselves, okay? So they're still going to be distinct, separate noodles, but they're going to be kind of arranged in a random order. And that's what we see here with thermoplastics. Now, if you contrast that with thermosets, the main difference between a thermoset and a thermoplastic is that the noodles, let's say, the spaghetti noodles, are going to be linked together. So we have this cross-linking. So now we have individual spaghetti noodles that are linked to other spaghetti noodles. Okay, and I know that that's not traditionally how spaghetti noodles are, but that's the difference between a thermoset and a thermoplastic. And it also identifies how their behavior is different. Okay, the thermoplastic is going to heat up. As you heat the thermoplastic up, it's going to soften. And then when you cool it back down again, it's going to reharden. And you can do that cycle over and over and over again. So heat it up, it softens, it cools, and it hardens. A thermoset does not behave that way. A thermoset really has one shot. When you heat up a thermoset, what happens is it just, it burns or it gets destroyed or it doesn't reform. Okay. And that's a good way, to look at if you want to know whether an object is a thermoplastic or a thermoset, is heat it up. If it melts and then you can reform it, then it's a thermoplastic. If you heat up a thermoset, it's going to burn. All right. The other way that we can describe a polymer, right? In this case, a thermoplastic, is whether it's amorphous or semi-crystalline. Okay. There's actually a third type. There's crystalline, but we're not going to talk about crystalline right here. So we're just going to look at the difference between amorphous and the semi-crystalline. So with amorphous, notice the strands are kind of randomly oriented, right? These are the molecular, the molecular strands. Semi-crystalline, we have a semi-organized molecular structure to it. All right. So remember that as we talk a little bit later about the difference in production between amorphous and semi-crystalline. Okay. So now, looking at thermoplastics, focusing in on thermoplastics. Okay. Remember, we have this continuous cycle. So that differentiates thermoplastics from thermosets. That you can heat them, they soften, they cool down, and they harden, and then you can repeat that cycle. All right. Thermosets, you can't. So we can view the different types of thermoplastics, thermoplastics here. On the left-hand side, we have amorphous thermoplastics, right? And so these include commodity plastics at the lower level. Commodity plastics are just cheap everyday plastics, okay? Engineering plastics. So here we're getting a little bit more, a little bit better material properties, a little bit better heat and chemical resistance. As we go up, we get higher temperature plastics, and then we get to extreme temperature plastics. So as you're going up here, you're getting better quality, better material properties. These at the top are called high performance engineering plastics. And so on the left-hand side, we have the amorphous thermoplastics, and on the right-hand side, we have the semi-crystalline amorphous plastics. Okay. All of these are just the common abbreviations for these. Some of these, PC is polycarbonate, PS is polystyrene, PVC, polyvinyl chloride. Those are common in pipes, like in your house, in your plumbing. I can't think of anything else down here that isn't known. A lot of these are just known by their name. And this is polypropylene, PP, polyethylene, PE, PET, PEEK. These are known by their abbreviations. Okay, and I'm not going to go into the different chemical names because, frankly, I don't know them all. So I know them by their abbreviations. All right, so focusing in on the thermoplastic behavior. What we're interested in is understanding how the thermoplastic behaves when it's heated, okay? Because that's how we're going to cast it or mold it. Basically, we're going to heat it up, and then we're going to shape it with a mold or a die, and then as it cools down, it's going to take on that shape. So what we need to understand is there is a difference between amorphous, right? And that's this line right here, amorphous plastics, and semi-crystalline plastics, okay? So think of semi-crystalline plastics as melting like ice, all right? So ice, if you think about how it melts, you got the ice cube, and then when you heat it up to a sufficient temperature, it just melts, right? It's going to kind of dissolve and kind of melt into the into kind of a liquid form, or it's going to flow. With an amorphous thermoplastic, it's going to melt like frozen butter. All right. That is to say, it's going to melt very quickly, and it's going to go from a solid straight down into where this is called a rubbery material. Okay. So semi-crystalline is going to melt a lot like ice, where it's, if you think of ice melting, it's going to kind of gradually create this pool of water, right? In this case, we're not creating a pool of plastic, but it's going to gradually get more and more rubbery, right? And you can see that from the curve here, right? It's not a sharp downward curve where we go from, on the y-axis is stiffness, where we go from, being kind of solid to, it's all the way down here till it's rubbery, like a noodle, like a wet noodle. Here, it's going to take some time to get to this temperature. All right. So we note here different temperatures for different materials. So with the amorphous thermoplastic, we have what's called the glass transition temperature. Right. This is the glass transition region right in here. And this is where we go from a glassy material to a rubbery material where it's kind of like a wet noodle, right in that region right here. Notice that the semicrystalline doesn't really have anything to do with the glass transition temperature. It goes right through it. Even though it is losing some of its stiffness, it is getting a little bit rubbery. It comes in here, and right in this region where we start to have a sharper decline, we call that the melting temperature, okay? And that's where we do get a sharp decline here. So here we have a gradual decline, and then at the melting temperature for semicrystalline, it goes down to a sharp temperature. And then down here with the amorphous, we have what's called the softening temperature. And this is where it really kicks over into a melted state. Okay. So, we're not going to get too much into the chemical reaction and the different temperatures and everything, but I do want you to be aware of the difference between thermoplastics and thermosets and how thermoplastics in this case respond to temperature. Okay. So when we talk about injection molding, right, of thermoplastics, injection molding is going to occur after the T softening. So we have to heat up the amorphous plastics to this higher temperature, right? For the semicrystalline materials, injection molding occurs after T melt, or the melting temperature. So you'll notice that the melting temperature is going to be lower than the softening temperature, or the softening temperature for the amorphous. And so it requires less energy then to use semicrystalline with injection molding, because energy means that we're going to have to heat up the material more with reaching a higher temperature here for the amorphous. Okay. A little bit more about the difference between amorphous thermoplastics and semicrystalline thermoplastics. Amorphous thermoplastics are randomly ordered molecular structure. We showed that in the figure. They lack a sharp melting point, and we can see that right here. They kind of, all through the glass transition, they're kind of in there. The result is that amorphous materials soften gradually as the temperature increases. Okay. Here's some examples. Now here's the names, right? PMMA is polymethyl methacrylate, or also known as acrylic. Polystyrene, polycarbonate, polysulfone, polyvinyl chloride. ABS is another very common one that everyone knows it as ABS, but the actual name is acrylonitrile butadiene styrene. Boy, that's a mouthful. And then PEI is polyetheramide. Again, I'm not so good in pronouncing these, I guess because I'm not a chemical engineer or a plastics engineer. Looking at the pros and cons, why you would choose amorphous versus thermoplastics. Pros, they're easy to thermoform, good dimensional stability, they have good impact strength and structural application. They're good for structural applications. The negative aspects of amorphous, they're sensitive to stress cracking. They have poor fatigue resistance, right? Using them over and over again, such as bearings or something where they're going to be rubbed on. They're not so good. They also have high friction. That probably relates a lot to the fatigue resistance. And they have low chemical resistance. Now looking at semicrystalline thermoplastics, these are highly ordered molecular structures with sharp melting points. They remain soft until a certain quantity of heat is absorbed and quickly change into a low viscosity liquid. This melting point is generally higher than the amorphous plastics. All right. We have polyethylene, polypropylene, polybutylene, terephthalate, PET, and PEEK. I won't try to pronounce those. These are important for you to know. These are the more common ones, right? Pros here: tough plastic. They're very tough plastics. Good wear resistance, excellent chemical resistance, good for structural applications. The cons here: they're difficult to thermoform. They have poor dimensional stability and poor impact resistance. All right. So, to summarize the thermoplastic behavior with a specific kind of focus on injection molding, polymers melt and become very viscous, 2 to 20 times that of like molasses, which is already viscous enough. So, they don't flow well. So that means we have to inject them at very high pressures. All right. The longer molecular chains, the more viscous the melt. Right. And basically the longer the chains, let me go back here. These top high performance engineering have longer chains than these lower ones, the commodity plastics. All right. So longer chains means higher molecular weight. Viscosity drops with increasing temperature. So that means you heat it up more, you're going to get lower viscosity. But obviously when you heat it up more, that requires more energy, more time. So there's trade-offs there. And of course, you can degrade the plastic if you heat it up too much. You can't, even though it's a thermoplastic, you can't actually heat it up too much. And then obviously cooling time also increases with temperature. So you heat it up high, it takes more time, it takes more energy, and then it takes more time for it to cool down. So generally speaking, injection molding is done around 100 degrees Celsius or 212 degrees Fahrenheit above the T softening for amorphous or T melting for semicrystalline. So about 100 degrees above TS and TM. All right, now focusing on the process, injection molding. This is the most important manufacturing process for industrial design, right? Not casting, not forging, but really injection molding. And when you look around, nearly everything, especially everything that's plastic, is made from injection molding. It's very, very common, very easy to do. You got a wide range of materials, a wide range of applications, you can control different material properties, all that good stuff. You get a huge form freedom, potential for functional integration. That means we can integrate different things like threads. We can put metal in here. We can do different types of insert and outsert molding. And it's relatively high production speed, much higher than metal casting. All right. Thermoplastic and thermoset polymers, otherwise known as plastic, have a broad range of material properties. And here's some pellets. They typically come in this pelletized form. We get unlimited colors, right? Levels of transparency, so clear all the way to opaque, and variety of textures. All right. As I said, in this lecture, we're really going to focus on thermoplastics. So what does a plastic injection molding machine look like? Well, it looks like this machine on the right-hand side. All right. So we have a ram or screw thread here that's going to inject. This hopper has the plastic, the pellets. The hopper is going to distribute the pellets into the screw thread here where it's heated. The screw thread is then going to force the plastic into this area in here behind this chamber, and this is where we have our dies. Okay, so these molds or dies are very expensive because we need to machine these. We need to make these out of hard metal, and they need to have a high accuracy, right? If we don't have a high accuracy on these, then we're not going to get highly accurate parts. And a high accuracy on these parts means a lot of money, right? These are very expensive and they don't last so long, so they do need to be replaced. They do need to be finished up every once in a while and kind of you know, taken care of. You might have some degradation in the surface that needs to be addressed. So a schematic of the plastic injection molding machine is shown here. This is a little bit backwards from this one, right? This one, the screw is moving from the right to the left. Here, whoops, let's go back here. Here we're injecting it from the left to the right, but other than that, it's the same. So here's our hopper where we put our pellets. The pellets are distributed or dropped down into the screw, the reciprocating screw, which is just going to rotate. So the screw is rotating, and notice these like screw threads here are going to feed the pellets into this chamber right in here where it's going to be injected. Now, the screw thread is also heated. This whole chamber is heated, and actually I think you can see these little rectangles above and below. Those are signifying the heating elements, right? So this whole area is heated. So the pellets are going to gradually get softer and softer until they melt at this end right here. And then the screw thread is going to push the plastic, the molten plastic now, into the mold. So you can see it coming in here. It's going to go into the mold. When it's done, the mold is going to dislodge from the flow here. The mold is going to open up, and then there's going to be ejector pins that are going to push out the object. Okay. I encourage you to look at the videos that I included in Canvas. I have a lot of videos on injection molding that are, I have some animations, and I have some actual injection molding machines in the videos. So it's very informative for you. So the process goes like this. One, the first step, the nozzle injects the melted plastic through the sprue, right? So here's the sprue right here. The plastic is coming in this way. So you can imagine the plastic is the blue here. So the plastic is going to be injected through the sprue, through the runners and gates. Now that should sound familiar from the metal casting. Through the runners and gates into the different chambers where the part geometry is. So the cavity is filled through several narrow gates. After sufficient cooling, the die halves are separated. So these die halves, the upper and lower, they're not called cope and drag now, but the upper and lower die halves are separated. The part is pushed out of the mold with ejector pins, and these are the ejector pins right here on the left and right hand side. So they push the part out. The die halves then close, and the process repeats. So 1, we fill it. 2, we allow it to cool slightly, right? 3, the mold opens. 4, the ejector pins push the part out and the part falls down into the bin. Here's an animation of that. Okay, so that's the injection molding process. The cooling and ejecting part of that is up to 50 to 70% of the total cycle time. Okay, so it's a substantial part, the cooling and ejecting. Think about doing hundreds of thousands of parts, right? So doing one part, you might think that the cycle time, the cooling part of it is just going to be seconds, right? Maybe at the most a minute. Well, probably not a minute, but definitely seconds. But when you multiply that by hundreds of thousands of parts, then you get to see a substantial cycle time contribution, and that's where a lot of money is spent on cooling the parts faster and faster. Shorter cycle time equals faster production is lower, means lower dollars per part. So cooling time dependent on part geometry. Plastics cool much slower than metals, right? 400 to 800 times lower thermal conductivity for plastics. And part thickness strongly influences cooling time. So the thicker the part, the easier its ejection will be, right? Because it's not going to be floppy, but the longer its cooling time. So it's a little bit of a trade-off here. As I think we've seen with most of the manufacturing processes so far, there's always a trade-off. All right, now I do have one video in here that I'm gonna show you here. This is we're gonna look at different phenomena that happen, that occur in an injection molding process. The first one we're gonna look at is jetting. Okay, so jetting is not something that you want. Jetting is what happens when basically the plastic, in its first initial press or push into the mold, is going to kind of jet into the mold. So it's going to spray into the mold, and then the rest of the plastic is going to come around. And that creates an undesirable surface. So let's watch this video real quick. So you can see the jetting occurs in there, and then the rest of the plastic is going to flow in behind it. So here you'll see it. So the jetting and then the rest of the plastic. And what happens is you get that undesirable kind of shape on it, or lines. So that's something that we try to avoid. And basically we do that by either lowering the viscosity or decreasing the pressure of the screw thread and injecting the plastic. Another phenomena, another problem that we have with injection molding is knit lines or weld lines. Okay, this is where we basically have think of the plastic being injected into the mold as kind of having a wave front, right? So it's kind of like water, where if you spill water on the floor, the front edge of the water is going to be that wave front. So that's what we have here. And when we have certain obstructions in the die, right, in the mold itself, and these are part of the structure of the die, so we can't get rid of these. But what happens is they're going to create an obstruction that then the material is going to have to reform around. So let's say we have this square obstruction. The plastic is injected from the bottom, and it's going to come in here. It's going to hit this obstruction, and then we're going to create two wave fronts of the plastic. And then the plastic is going to be, basically, this is what creates the weld line. It's going to be stitched together on the back side of this obstruction. And then this is going to create the weld line or the meld line. And we can see that here. It's undesirable, especially in parts where the surface, it needs to be of high quality. We can see some here. So here, these on the right-hand side are very obvious, right? And you can see, basically, this little part right here indicates where the plastic was being injected to start with. So the plastic came in here. We had this hole that it has to go around. So it went around this obstruction, and then it welded on the other side of that, creating this line. We have the same thing here. The plastic comes in this way. We have these weld lines, and then it's not so good. All right. More weld lines here, more weld lines here, you know. So it's not always something that is going to make a part unusable, but it depends on the application of the part. If it's something where the surface is seen, it needs to be nice, then these aren't going to be good. We also, like with metals, we also have shrinkage, residual stresses, and different factors like that. Thermal expansion of plastics is about 5 to 10 times that of metals. Okay, so they cool slower. So this, in this, or I guess this graphic taken from an animation, we can see the hot center of the plastic right here, where the rest of it is cool. And this is going to create what are called sink marks. So we can see those here. These sink marks are basically where the plastic was this bit was the last area of the plastic to cool and solidify. And again, it depends on the application. It depends on the part, whether this is going to make it so the part is not usable or whether this is just fine. Right. Injection mold design. So the mold itself is considered a separate and very complex machine for injection molding. Right? You can just see in this image right here. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 16 different parts that we're going to inject, or excuse me, that we're going to create on one injection. All right. The plastic is going to be injected in here. right? We can see, where's the, oh, excuse me, we can't see, can we see that? I don't think we can. It's going to be injected right there, okay? So these 5 holes right here, these 5 holes here and here, this is where the plastic is going to be injected, all right? It's going to be injected, and then it's going to go through these runners, right? This kind of X-shaped runner for each one of these, and then it's going to go through the gate into the part, right? So these molds are going to be, they have to withstand very large forces. They have to last for a long time, about 1 million, what they call shots, when that's one injection is a shot. So about 1 million. Typically, they're made out of hardened material, tool steel, or in some cases, they're made out of aluminum, but aluminum is going to degrade faster than tool steel. It would be a cheaper mold, but it's not going to last as long. There's different types of injection molds. You can have a 2-plate mold, kind of like what we see here. We can have a 3-plate mold where we have in between the injection side and the ejection side, we have what's called a stripper plate, and this is just going to help remove the gates and runners here, the runner right there. And then we can have a hot runner mold where the injection side of it is going to have some heating elements to keep this area hot, right? And that's going to help remove the sprue from the product. And again, the aim here is to cut down on the post-production time, right? Because if we look at the 3-plate mold or even the 2-plate mold, this sprue right here has to be removed. So that's going to take time, right? Here, if we can get rid of it without having to manually remove it or have a machine to remove it, then we're better off. Parting planes. Just like in castings, parting planes exist on injection molding machines. They help determine the required clamping force and therefore the size of the injection mold. We have draft angles, right? This is an example of a part without a draft angle. And what's going to happen with this kind of part, because we made the mold without a draft angle, is we're going to be pulling a vacuum up in here, which means the part is not really going to come off really well. Here with draft angles, right? That's a draft angle on the sides, draft angle on the inside. The part is going to eject much more cleanly and easier. All right. So we're going to stop part 1 right now. That's been about 30 minutes, and we'll pick it up where we left off